Okay, we are welcome to Success Jam class. Today is Monday, 17th of February 2025. And today we have chemistry in our Jam class. And last week we started our Jam class last week where we're treating past exam questions. But today we want to go into some key topics in Jam chemistry. Some very important topics in Jam chemistry. We're preparing for Jam. So while you're reading, you should have these topics at the back of your mind. They are important topics that must come out in Jan one way or the other every year. They must come out in Jan one way or the other every year. So we'll look at the key Jam topics. We'll look at organic chemistry. Organic chemistry is a key topic in Jam. Organic chemistry. Gas laws. Question on gas laws. It's a key chemistry topic in Jam. Question on reaction stoichiometry. All possible questions on reaction stoichiometry. When this reacts with this to give this, find the mass of this formed, find the mass of that formed, reaction stoichiometry. Question on concentration of solution and solubility. Concentration of solution and solubility. Another interesting topic in Jam is electrolysis. These are key Jam topics: electrolysis, electrolysis, electrolysis. Another key aspect of Jam is experimental chemistry. This is one aspect that students struggle with: experimental chemistry. In this aspect is dealing with all this calcium and the color of the ion, white, which of this produces white. When reacting with this, if we open Jamb chemistry exam, some of the people produce white coloration. Experimental chemistry, very important aspect of chemistry we're going to look at. Experimental chemistry. We've looked at acid, base, and salt. Acid, base, and salt. Nuclear chemistry. Nuclear, we have nuclear fusion, nuclear fission. That's under radioactivity, nuclear chemistry. Nuclear chemistry, when we talk about the alpha, beta, and gamma rays, when an atom undergoes radioactive decay, it splits into half its original mass, and then you have to find the half-life of that material, radioactive material. We're going to look at when an alpha particle is emitted, what amount of the radioactive element is remaining. When a beta particle is emitted, what's the effect of an alpha particle, a beta emission, or a gamma emission? We'll look at it under nuclear chemistry. So you look at nuclear chemistry, look at electrolysis, look at organic chemistry, look at reaction stoichiometry. We'll look at chemical equilibrium. Chemical what? Equilibrium. And rate of chemical reaction. And rate of what? Chemical reaction. And rate of chemical reaction. If I open any Jamb chemistry exam question, I'm likely to find a question on one of these topics there. Very interesting. If you see now, they say the density of a certain mass, this gas law already. This gas law. What is the molar mass? More. That's under stoichiometry. Stoichiometry is broad. everything involving stoichiometry, number of moles, Avogadro's number, reactions, everything isotopy, we'll treat it under this, number of moles, amount of substance, everything is involved there. Molar mass, percentage composition. We're going to broaden this reaction stoichiometry to empirical formula, molecular formula, you know, everything they can possibly ask you under reactions, elements, are we together, number of protons, the neutrons, the electrons. So this is a very broad aspect. This is a very broad aspect of reaction stoichiometry. This gas law is also very broad. And organic chemistry is, in fact, is half of chemistry. Because if you're looking at chemistry as a whole, we have the organic and the inorganic chemistry. Every other thing you're treating in chemistry is inorganic. All these things are inorganic. So organic chemistry is, when you mention organic chemistry, is a broad topic on its own. Because you look at cracking that happens in organic compounds. You understand? Look at a lot of things that happens. Octane number, octane rating of organic compounds and all that. We look at a lot of things under organic chemistry. So organic chemistry is broad. It's a broad topic on its own. Then you have nuclear chemistry, is another aspect of chemistry that you will look at. If you know some of these key topics in chemistry, you find out that you can answer most questions in your Jamb. Look at this. What weight of NaCl is needed to make 2.0 DN cube of a 1.5 m solution? Solution, concentration of solution, solubility. If you just open any question, 0.5 mole per DN cube of ACl visualized by this is under concentration. Now we use CAVA all over CBVB equals to Na over Mb. Concentration, titration, acid, base, and salt. Look at buffer capacity, buffer solution, acids, base, and salt. Types of salts. We have normal salt, we have acidic salt, basic salt, double salt, and complex salt. 5 types of salt we have. That's under types of salt. Base, look at base, look at acid. That's under the aspect. So you see that any question you're being asked here is linking to one topic here or the other. Is linked to one topic here or the other. Now, class, I would like us to quickly start today's chemistry class. Let's take today's chemistry class. Let's take one of these topics and we'll take it from there. Are we together? Let's take one of these topics, take it from there. So you have your Jamb chemistry, you have organic chemistry, you have what? Okay, so let's look at organic chemistry. Let's look at what? So of course we'll take all of them. So let's take one of these, our direction. Let's take them one after the other. So we can tick them off one after the other. Okay. So I think let's start with organic chemistry. Let's refresh your memory about everything that's with organic chemistry. As we're taking it, we'll also take Jamb questions on them. Organic chemistry. Let's start with organic what? Chemistry. So these topics I gave you on your own, on your personal reading, make sure you're also furthering on them. Jamb loves all these kind of topics a lot. Jamb loves all these kind of topics a lot. Okay? So when looking at organic chemistry, let's write down organic chemistry. When we look at organic chemistry, we're going to study organic compounds. Organic compounds. Or the compounds every compound in organic chemistry is called an organic compound. The compounds we study in organic chemistry are known as organic compounds. The compounds we study in organic chemistry are known as organic compounds. The compounds we study in organic chemistry are known as organic compounds. So let's look at what are organic compounds. Organic compounds are compounds of carbon and its derivatives. Organic compounds are compounds of carbon and its derivatives. Organic compounds are compounds of carbon and its derivatives. So when you find organic compounds, organic compounds are compounds of carbon and its derivatives. Very short definition of organic compounds. Class, before now, we define organic compounds as compounds that are naturally occurring. Actually, in the real sense of it, organic, this word organic means naturally occurring. When something is naturally occurring, is what? Is organic. That means it was not artificially synthesized. That means it was not artificially what? Synthesized. When something is naturally occurring, we call it what? Organic. When something is naturally occurring, we call it organic. That means it wasn't artificially synthesized. It's just occurring naturally. In other words, it's not man-made. It's not man-made. So say their naturally occurring compounds are organic. But you know why we stop using using this to define organic compounds? Because we found out that there are some organic compounds now that are not naturally occurring. They can be synthesized by man. There are some compounds that are not naturally occurring. They can be synthesized by man. So because of that, we stop defining organic compounds as naturally occurring compounds. Because, for example, a good example of organic compound is urea. Class, urea is a major component of your urine. And before now, we thought that urea as an organic compound, since we say organic compounds are naturally occurring, it means that they are not man-made. They are not man. So we thought that all organic compounds cannot be made by man. But class, to our greatest surprise, I think F. Wohler, a scientist known as F. Wohler, Frederick Wohler, in the year 1828, was able to synthesize urea from the rearrangement reaction of ammonium cyanate. Ammonium cyanate undergoes rearrangement reaction and was able to give rise to what? Urea. Urea is a major component of your urine. So it means that if you can make urea, you can make urine. Because apart from urea, the other things in your urine is just liquid water and ions, sodium ions, those other ions that during ultrafiltration of your Barman's capsule, your kidney, your nephron, your Barman's capsule, they help to what? To undergo ultrafiltration, and maybe the excess ions will be in your urine, you understand? The main component of your urine is your what? Your urea. So because urea is an organic compound and it can be synthesized by man, it defeated the definition of organic compounds as naturally occurring. So we started defining organic compounds as compounds of carbon. This one is sure. This definition has not been defeated because all organic compounds contain carbon. We found that when you're defining something, a definition must contain something that is it's all encompassing. No matter how you look at it, it's correct. So this is not correct by saying organic compounds are naturally occurring because urea is not completely naturally occurring, can now be synthesized by man, right? So we cannot say all organic compounds are naturally occurring. We can't say that anymore. So but we can say all organic compounds contain carbon, class. You cannot be an organic compound if you do not contain carbon. You cannot be an organic compound if you don't contain carbon. So we say organic compounds are compounds of carbon and its derivative. Very, very important. Now moving forward, having defined organic compounds, we're going to introduce you now to the first three families of organic compounds. First three families of organic compounds that we have. Just like when you go to inorganic compounds, you have elements, compound, and mixture. You start breaking it down from the types of compounds, mixture elements. Elements are very into metals, non-metals, semi-metals, right? Also, in the organic chemistry world, we also have organic compounds. And organic compounds have three major families first. The alkane family, the alkene family, and the alkyne family. These are the first three families of all organic compounds. These are the first three families of all organic compounds. The alkane family, and the alkyne family. Alkane, alkene, alkyne. So organic compounds are first classified into alkanes, alkenes, alkynes. We have other families, of course, but these three families are the most popular family of organic compounds. These three families are the most popular families of organic compounds. The alkane family, we call them the paraffins. The alkane family, we call them the olefins. Here we have the acetylenes. This is their second name. And when naming organic compounds, members of organic compounds are named based on the number of carbons they contain. Members of organic compounds are named based on the number of carbons they contain. Class, if an organic compound contains one carbon, the naming will start with met. If it contains two carbons, it starts with et. Three carbons, it starts with pro. Four carbons, it starts with but. Five carbons starts with pent. Six carbons starts with x. Seven carbons starts with ept. Eight carbons starts with oct. 9 carbons starts with non. 10 carbons starts with dec. So class, the number of carbons an organic compound contains will determine how the naming will start. For one carbon organic compound, the name will start with met. For two carbon organic compound, it starts with what? Et. So the number of carbon an organic compound contains determine how the naming will begin. So if you see an organic compound with met, starting with met, just know that that organic compound contains one carbon. If you see an organic compound starting with et, know that the organic compound contains two carbons. Pro, it means the organic compound contains three carbons. But, the organic compound contains four. Pent, five carbons. X, six carbons. Ept, seven carbons. Oct, eight carbons. Non, nine carbons. Dec, 10. But class, that's the beginning of the naming. What determines the ending is the family you belong. What determines the ending of the name is the family you belong. Let's have here alkane. Let's have here alkene. And let's have here alkyne. Class, what determines how you start is the number of carbons. What determines how we end your naming is the family you belong. Class, if you're under the alkane family, you'll be met. First carbon. But your naming will end with AN because you're on the other the alkane, ANE. Class, of course, there's no first carbon member for the alkene and alkyne family. They do not have one carbon member. Their first member starts with two carbons. So if you have two carbons under alkane, you will be et because you have two carbons. But because you're under alkane, you'll be ethane. If you're under alkane and you have two carbons, you'll be et again because it's two carbons, right? But your naming will end with ane instead of ane. This one ends with ane, A-N-E. But this one ends with E-N, in. If you have two carbons and you're under this family, you'll be et. But what will it be now? Ine. Because YN. So what determines the ending of your name is the family you belong. But what determines the beginning of your name is the number of carbons the organic compound contains. So the beginning of the naming of an organic compound is dependent on the number of carbon. Number of carbons determine the beginning. Number of what? Carbons determine how we start to name the organic compound. But the ending, what ends the name is the family you belong, right? The family of the organic compound determines the ending. So look at these three compounds, et. They all start at the same beginning, right? Because they all have two carbons. They all have the same beginning. But look at the ending. N, in, ein. N, in, ein. Are you seeing it? Now, if you have three carbons and you're under this family, you'll be pro. Under this family, you also be pro. Under this family, you also be what? Pro. But watch. Here, you're going to be propane, propene, propine. So you can see the ending. They started the same way, but they're ending differently, depending on the family they belong. Class, you can apply this same approach to all 10 prefix, all of these 10. So if it is 4, it will be butane, butene, butine. If it is 5, it will be pentane, pentane, pentane. If it is 6, it will be what? Hexane, hexane, like that. If it's 10, decane, decane. Class, this is the naming of each of these three families, but that's not all, class. In organic compounds or in organic chemistry, there are three things we seek to know. Number one is nomenclature of an organic compound. Anytime you are dealing with an organic compound, you want to know how to name it. Number two is the molecular or chemical formula. Let's look at the molecular what? Formula. The molecular formula. And number three is the structure. Before you now look at how does the organic compound react, react. Class, these are the four bases of everything we'll study about each organic compound. These are the four bases of everything we'll study about each organic compound. The naming, the nomenclature, how to name the organic compound, which we are teaching you that the beginning is the number of carbon, the engine is the family it belongs, right? 2 is the molecular formula. Molecular formula. 3 is the structure, how to draw the structure. And 4, how does the organic compound react? The chemical reaction, how does it react? When it reacts with this, does it obtain? When it reacts with this, what does it obtain? How does it react? Class, these are the 4 things you should seek to know when studying any organic compound. These are the 4 things you should seek to know when studying any organic compound. So class, what we are doing here now is teach you how they are all named, how each of these organic compounds are named. The next thing we want to look at now is their molecular formula. They are what? Because it's one thing to know that this is methane, but it's another thing to know the formula. For example, in inorganic chemistry, no, we're dealing with organic chemistry. In inorganic chemistry, we say sodium chloride. Sodium chloride is the name, right? But the molecular formula of sodium chloride is NaCl, right? And I can tell you that sodium chloride can react with so and so to give this. That's a reaction. So that's the same thing we are doing in organic chemistry. So it's not enough to just know the name. It's not enough to just know the what to name. We want to know the molecular formula. And class, to understand the molecular formula of each of these families, we must understand that each of these families have their general formula we use to get their molecular formula. Each of these families have the general formula. Class, general formula helps you to determine the molecular formula of each member. General formula helps you to determine the what? The molecular formula of each member of a family. In the alkane family, the general formula is CN H2M plus 2. In the alkene family, the general formula is CN H2N. And the alkyne family, general formula is CN H2N minus 2. Class, general formula is very important to help us to determine the members of each family. To help us to determine the molecular formula of the members of each family. Class, this N here represents number of carbon. You can see number of carbon, number of carbon. You see why carbon is very important when we're defining organic compounds. These organic compounds are compounds of carbon and its derivatives. Derivative means every other element can now be attached, but carbon is sure. In all organic compounds, carbon is sure, then any other element can be attached to the carbon. Now, class. So the number of carbon is still playing a role in the molecular formula. In the naming, number of carbon played a role, right? In the naming, if you are 1 carbon, you are met, right? If you are 2 carbon, you are et. If you are 3 carbons, you are pro. So in the naming, number of carbon played a role. Now, the molecular formula, number of carbon still plays a, because this N here represents number of carbon. So if we are to be asked for the molecular formula of someone like methane now, methane means 1 carbon, right? So using the general formula of our alkane family to be C1, because N is 1. N is, since methane is 1 carbon, N is 1. C1, H 2 times 1 plus 2. C1, H2 times 1 plus 2. C1 is C, of course. You don't need to say C1. C1 is C. 2 times 1 is 2. 2 plus 2 is 4. So you see that the molecular formula of methane is CH4. You see that the molecular formula of methane is CH4. If we try doing the same thing for ethane, ethane means 2 carbons. So anyway, you see N represents N is 2 now. That's C2, H2, N, which is 2 plus 2. That's C2, H, 2 times 2 is 4. 4 plus 2 is 6. So the molecular formula of ethane is C2H6 because N represents number of what? Carbon. So this general formula works for every member under the alkane family. This general formula works for every member under the alkane family. This general formula works for every member of the alkyne family. So class, with this knowledge, if I ask you to find the molecular formula of hexane, class, when you hear hexane, what family comes to your mind? Is it alkane, alkene, or alkyne? Alkyne, right? So class, X, when you see X, how many carbons comes to your mind? X means 6. So it means that N here is what? 6. Now, hexane, the general formula for alkyne, you will not use general formula for alkane to solve for an alkyne, right? The general formula for alkyne is CN H2N minus 2. And where N is what? 6. Because N represents the number of carbon. So anywhere we see N, we put 6. We're going to have C6 H2 times 6 minus 2. So we have C6. H2 times 6 is 12. 12 minus 2 is 10. So we have C6H10. We have C6H10. This is the what? Molecular formula of hexane. This is the molecular formula of what? Hexane. Class, moving forward, the next thing we want to look at now is how many bonds does an alkane family have? We want to look at the structures. An alkane family has single bonds all through. An alkane family has at least one double bond in the structure. And an alkyne family has at least one triple bond. So alkane families are recognized by the bonds, single bonds all through. The alkyne families have double bond, at least one double. It doesn't mean that they don't have single bond. They have single bond, but the presence of one double bond supersedes all the single bond in alkane and makes you an alkene. Class, as a compound, you might have several single bonds everywhere, but you have just one double bond. You automatically become an alkene. And the same thing applies here for alkyne, triple bond. The presence of one triple bond automatically makes you an alkyne, even if you might have other single bond. The presence of one triple bond makes you an alkyne. So alkanes are single bonded, alkynes are double bonded, alkynes are triple bonded. Alkanes are single bonded, alkene double bond, alkyne triple bond. Now class, I remember I listed 4 things. How these compounds are named, nomenclature. Nomenclature means naming. I've explained how to name each of these 3 families. 2 is what? The molecular formula, which you have also done. By knowing the general formula, you can get the molecular. With the general formula of each family, you can get the molecular. This one was CnH2n minus 2, right? Class, just the general formula can be asked of you in the exam. Which formula is the correct general formula for the alkane family or the alkyne family? Just general formula alone can even be asked of you in the exam. So it's important you note it. It's an exam question on its own. Even without the application, just the knowing that alkane is CnH2n plus 2 is a possible exam question. After knowing the molecular formula, you must now know how to draw the structure. How to draw the what? Class, it's good that methane is the name. It's good that CH4 is the molecular formula. Now, what is the structure of CH4? Then after structure, reaction. How does CH4 react? Because class, the alkane family have a peculiar way they react. So we're going to look at reactions of alkane. The alkene family have the peculiar way they react. So we look at reactions of alkene. And the alkyne family has a particular way they react. So we look at reactions of alkynes. So we're looking at reactions of alkane, and alkynes. So class, structure. Structure, we're looking at structure. Class, it's important to note that the typical alkane structure is tetrahedral. The typical alkane structure is what? Tetrahedral in shape. A typical alkane molecule is tetrahedral in shape. A typical alkane molecule is trigonal in shape. And a typical alkyne molecule has a linear structure. Class structure will dictate how the typical structure of each family will dictate how the structure will come out of each member. So class, if we are to draw the structure of methane, for example, class, carbon is usually the central element in all structures of organic compound. The first element drawn when you want to draw the structure of any organic compound is carbon. So I want to draw the structure of methane. I'll first start with carbon. I'll put only one carbon because I already know that met means one. If it was earth, what will I do? I'll put two and I'll use a bond to join two of them. Carbon first. Carbon what? If it's pro, three carbon, I'll put another bond to join the three of them. If it is four carbons, what do? Another one. Are we together? So when you want to draw the structure of any organic compound, start with carbon. Remember that carbon is the alpha and omega of all organic compounds. Now, class, before we do the structure, I want to remind you of the configuration of carbon. Carbon is a very special element. It's number 6. The position of carbon on the element table is number 6. If you have hydrogen, helium, lithium, beryllium, boron, carbon. Hydrogen, helium, lithium, beryllium, boron. So carbon lands exactly on number 6. And which gives it a peculiar configuration of 2 and 4. Don't forget, when writing electronic configuration of carbon, we have 2 electrons are stored in the K shell and 4 electrons are stored in the L shell. So class, from our foundation in secondary school, we remember that I'd like you to recall that for carbon to attain an octet state, it requires 4 more electrons. Because every element wants to attain an octet state of 2 8s. Because this L shell is not completely filled, class. The L shell requires 8 electrons for octet configure. But currently it has only 4. So 4 more electrons are needed to ensure its complete configuration, its octet configuration. Class, because carbon is always looking for 4 electrons, it will also show when it's trying to bond with anybody. So when drawing the structure of organic compounds, you must ensure that every carbon in the organic compound has exactly 4 bonds. Any organic structure with any carbon that is not up to 4 bonds, you're already having a wrong organic structure. Every carbon in the organic structure should have 4 bonds. Because of this explanation I just gave to you, carbon is 2, 4. So it will require 4 more electrons to attain an octet state. Hence, when you draw the structure of each carbon, it must contain 4 bonds. If this compound was ethane, which is 2 carbons, class, this other carbon must still have 4 bonds. So before you even determine what to fill up all these spaces, first get the bond structure correctly. Are we together? It's wrong to draw a compound and you will not do something like this. This is just 3 bonds, and it is free. You're not done. In fact, you're not obeying the octet rule. There's what we call the octet rule. Class, when drawing structure of any compound, the octet rule must be obeyed. The octet rule must be obeyed. Now, class, we're still trying to draw the structure of just simple methane. So I have put carbon here and you put 4 bonds. So you now know that anytime you draw an organic compound, put carbon and must have 4. Now the bonds we filled up with hydrogen, class. Class, after carbon, the next common element in all organic compounds is hydro. After carbon, the next common element in all organic compounds is what? Hydrogen. Hydrogen is the next common element in all organic compounds. And you can see this is the structure of methane. You can see why we say it's tetrahedral. Tetra means four, tetrahedral shape. It's important to note that each of these families have their most important member. Yes, they contain many members, but they have their most important member. The most economically important members are usually the first member. Plus, the most important member of the alkane family is methane. Most important member of the alkane family is the ethene. And most important is ethine. So they have their most important member. Every family has their most important member. Most important member is determined by who is more economically important. It's all called economical importance of organic compounds. Who is more economically important? Now, class, moving forward, we can as well draw the structure of ethane. Ethane means two carbons, means that we increase the carbon length to 2 and make sure that every carbon still have what? 4 bonds. Look at this carbon, 1, 2, 3, 4. Look at this carbon, 1, 2, 3. Of course, this bond is being shared by these two carbons, right? So when counting for this carbon, you count this bond. When counting for this carbon, you still count this. Because it's for two of them, it's for 12. So class, every carbon must have 4 bonds in a correct organic structure. Looking at this carbon, you have 1, 2, 3, 4. Looking at this carbon, you have 1, 2, 3, 4. Now, class, if you are to increase the carbon length to 3, this is propane. You see that every carbon still has 4 bonds. If you check it well, every carbon still has 4 bonds. If you want to go to butane, the same thing. Increase the carbon length. Increase the carbon length. Butane. Butane. Are we together? Now, if you want to go further, you keep going on and on and on. That's the alkane family. Now, what if this was alkane? Let us draw ethane, for example. Ethane. Ethane means 2 carbons. Et means 2 carbons. In means double bond. Yes? Which one? I'm just increasing the carbon length, that's all. When it's 1 carbon, this is methane. Hydrogen, hydrogen, hydrogen. Right? Now, et means 2 carbons, right? You have to clean 1 hydrogen there and increase carbon length to 2 carbons, and continue the hydrogen, fill hydrogen on every side of the carbon. Now, if I want to go to propane, all I do, I'll clean this hydrogen in front and increase the carbon length, right? Then fill the other space what? Hydrogen, hydrogen. That's why I just did propane. Now, if I want to go to butane, the 4 carbon butane, I'll just clean this hydrogen here and increase the carbon length. Do you understand now? So this is how you draw the structure. You keep going till you get to deck 10 carbons. So alkane, typical structure of the alkane family is very simple. The typical structure of the alkane family is very simple. Let's go to alkene now. For the alkene family, there must be presence of double bond. So class, they cannot be a 1 carbon member. You know why? Because carbon cannot have double bond with hydrogen. It's not possible. Hydrogen just needs 2 electrons to be stable. So giving it 2 bonds is giving it 4 electrons. Because class, for every bond that is between 2 elements, it contains 2 electrons. A bond is worth 2 electrons in chemistry. So if you have 2 bonds, how many electrons are here? 4. Do you understand? 1 bond gives off 2 electrons. Are you with me? 1 bond represents what? So what's 2 bonds? 4 electrons. And that will overwhelm hydrogen. Hydrogen is number 1 in the element table. It just needs 1 more electron to attain duplet configuration. Hydrogen does not want to obtain octet configuration. It wants to obtain duplet. So it just needs 1 more electron. It just needs 1 more electron. So you cannot have double bond. Carbon cannot have double bond with hydrogen. That's why 1 carbon Alkane does not exist. So there's nothing like methane. There's nothing like what? Methane. There's nothing like this. And there's nothing like methane. So the first member starts on 18. So you how do you draw 18? Two carbons, and in between the two carbons you put double bond. Two carbons, and in between the two carbons you put what? Double bond. Now don't forget that each carbon must always have four bonds. So class, if there's already two bonds, how many more bonds can this carbon have? Two more. One, two. These two bonds also contain for this carbon. So this carbon can also have only two. Every carbon must have four. Once you've gotten the bond right, fill up the bond space with what? Hydrogen. I told you after carbon, the next popular element in all organic compounds is what? Hydrogen. After carbon, the next popular element in all organic compounds is hydrogen. And class, this is the structure of what? 18. This structure of what? 18. Class, what if we ask the structure of propane? Propane is three carbons, right? I'll clean one hydrogen and introduce one extra carbon. Clean one hydrogen and introduce one extra, this propane, and fill up the carbon with hydro. Now watch. Someone would think that because we put double bond there, it means that everybody in our alkene must have double bond. No. Class, just this one double bond makes you an alkene. It's enough to make you an alkene. Even if there are single bonds everywhere in other places. One double bond is enough to make you an alkene. It's enough to make you what? It's enough to make a compound an alkene. So class, this propane now, this for these three carbons, carbon 1, carbon 2, carbon. So this propane. If it's butane, clean one carbon, increase the carbon length. You have butane. Do you understand? The same principle, the same principle. Now, what of alkynes? Alkynes are triple bonded. So as I said earlier, there's no met for alkyne too. It starts with two carbons because carbon cannot have triple bond with hydrogen. Carbon cannot have triple bonds with hydrogen. It's not possible. So it can only have triple bond with itself. So there must be two carbons for a triple bond to exist. There must be at least two carbons for a triple bond to exist. So after having your two carbons, you now ask yourself how many more bonds can each of these carbon have? Carbon must only have four bonds. So if you have 1, 2, 3, how many more bonds can this carbon carry? One more. Also this side, 1, H, H. So it means that this is C2, H2. C2 what? And this is ethyne. Class, you know the funny thing? From the structure, I can get a molecular formula because of my understanding. And if I still come here and use the general formula to get molecular formula of ethyne, I'll still land at C2H2 without drawing the structure. Remember they say Na2N minus 2, right? Ethyne means two carbons. Let me put N as 2 here. See, I'll still have C2H2. C2, Cn, right? So N is 2 now. H2N, that's 2 times 2 minus 2 minus, that's C2H, 2 times 2, 4. 4 minus 2. So we still have C2H2. But without using the general formula, because of my understanding of the structure, I still have C2H2. So you can use the general formula to get the molecular formula. If you draw the structure right too, you can still get the molecular formula. Are we together? Now, so this is ethyne. What do I do if I want to increase it to propane, 3 carbons? I will just clean one hydrogen on either of these sides and add one extra carbon. And add what? One extra carbon. I can just clean this hydrogen and put one extra carbon. But it's not compulsory that this carbon has triple bond. It's not compulsory that this carbon has triple. And this propane. This is what? Propane. If I want butane, I'll clean one hydrogen, add another carbon, and this butane. This is what? Butane. So you can just keep playing with it on and on and on. And you understand? It's your understanding that matters. It's your understanding that matters. Yes. You have a question? You have a question? Yes. You say? That was that was not alkyne now. That was alkane family. And it was for propane. This is a different family. Eh? Now, class, we have SPDF configuration. We have what we call what? SPDF configuration. Class, each of these families have how they are configured. The hybridization, let's call it the hybridization. Hybridization occurs in organic compounds, and we say hybridization is the mixing or interaction. Let's call it interaction between two orbitals. Hybridization is the interaction between two orbitals of carbon to form new orbitals. Hybridization is the interaction between orbitals of carbon. Is interaction between two orbitals of carbon. Hybridization is the interaction between two orbitals of carbon to form what? New orbitals. Hybridization is the interaction between two orbitals of carbon to form new orbitals. Class, the hybridization in our alkane family is the S, because look at, if you write down the electronic configuration of carbon, carbon is number 6. If I want to write the SPDF, yes, I also teach you guys the SPDF configuration. The SPDF configuration of carbon is actually 1s2, 2s2, 2p2. This is the SPDF configuration of carbon. 1s2, 2s2, 2p2. And class, there's actually interaction between the s orbital and the p orbital of carbon. That interaction will lead to new orbitals being formed called the sp3 orbital in the alkane family, the sp2 orbital in the alkane family, and the sp orbital in the alkyne family. Class, for your Jamb's scope, I do not need to go into details. If I was teaching 100 or 200 level, I will need to go into details to explain what caused the interaction between s and p orbital. But your Jamb's scope of study does not require that, does not require that. So it's just for you to know that the alkane family is sp3 hybrid hybridized, the alkane family is sp2 hybridized, and the alkyne is sp hybridized. Take a moment to write down. Continue. Tomorrow there will be a serious matriculation in school, so we'll not have class tomorrow. Please take note. School will be so crowded. Tomorrow is 100 level matriculation. Some of you may even have friends you want to go and celebrate with and all that. So tomorrow, please note, there won't be class tomorrow because of the matriculation holding in school. Even I've cancelled my 100 level class, cancelled all my classes tomorrow. You know how matric used to be in school, now everywhere will be crowded. So there won't be class tomorrow. Now, moving forward, I haven't understood hybridization. Another thing we need to understand is that for the alkene and the alkyne family, they can have more than one double bond. Class, look at this alkyne family. Double bond here and double bond here. Check, I still maintain that each carbon has 4 bonds. I still ensure that my carbon has 4. Count any of my carbons, you find that none of them is lacking. None of them is lacking less than 4 carbons. If you look at this carbon, you see 1, 2, 3, 4. If you look at this carbon, you see 1, 2, 3, 4. If you look at this carbon, you see 1, 2, 3, 4. If you look at this, you say 1, 2, 3. Every carbon must have 4 bonds. Plus, this organic compound contains 2 double bonds. So I'm going to say this carbon 1, 2, 3, and 4. Class, there's a double bond between carbon 1 and 2. We ascribe it to 1. Class, anytime we are naming organic compounds, we favor the lesser number. We favor the what? Lesser number. We favor the lesser number. Please be very careful. Your leg touch this thing. Move your leg from there. You shake this thing just now. Please. Please be careful of this. You want to stretch it, you can sit in another place. Between 1 and 2, give it to 1. Between 3 and 4, give it to 3. So class, this is 1, 2, 3, 4. So this is boot, of course. The naming starts with boot. We're not going to say 1, 3, boot 1, 3, die in, die. Die means that there are 2 double bonds present. Why do we say 1, 3? Because the first double bond is between 1 and 2. We gave it to. And the second double bond is between 3 and 4. We give it to 3. So this is now boot 1, 3, die. Why do we say die? Because there are 2 double. Die means double. There are 2 double bonds. Why did I write 3 as what? Yes. What should I have written? Why didn't you ask me why did I write 1? Why is it 3 that is the issue? Is that your question? How I counted it? Now, I said 1, 2, 3, 4. There are 4 carbons here, right? Each carbon has a number, right? Right? Now, this double bond there has to go to one of these 2 when you are naming. So there will not be confusion. You give it to the smaller number. Is 1 not smaller than 2? Between 3 and 4, we give it to 3 because 3 is smaller than. Was that your question? So we'll now arrive at both 1, 3 what? Die in. Of course, anybody that has double bond, his naming must end with in, right? But 1, 3 to show that the first double bond is on carbon 1. Second double bond is on carbon 3. So you have both 1, 3 die in. Are we together? Yes. Now, it's time to introduce you to another family called the alkyl family. The alkyl family are special because they have one origin less than the alkane family. So they have a general formula of CN H2N plus 1. Their naming end with YL. So if you have 1 carbon, you are methyl. If you have 2 carbons, you are ethyl. 3 carbons, you are propyl. 4 carbons, you are butyl. And you can keep going on and on and on, pentyl. Why is this family important? Because the next aspect we are about going to now requires us to understand this family, because in most complex organic compounds that will be giving us issues in their naming, this family occurs as a branch. They usually occur as a what? Branch. This alkyl family usually occurs as a branch. This alkyl family usually occurs as a branch. So they cannot stand on their own because they are lacking one less hydrogen. They cannot stand on their own, yes? You see? Alkyl family. No, it's plus 1. Alkyl family is plus 1, not minus 1. It's plus 1. Alkane is plus 2. So this guy is already having 1 more than this. If it's alkane, it's CN H2N plus 2. Alkane. So alkyl is just 1 hydrogen less. So that's why it's plus 1 instead of plus 2. It's not minus 1, it's plus 1. Now, class, these people are always occurring as a branch because they are not complete. Look at methyl, CN H2N plus 1. Let's apply general formula here. Met means 1 carbon. So you have C1, H2 times 1 is 2 plus 1, which is CH3. If you draw the structure of CH3, you see that you're going to have only 3 hydrogens. And carbon must have 4 bonds, right? So it's lacking here. Carbon is lacking here. What department? 111. All right, now welcome back. The alkyl families are very important because they occur as branches. They occur as what? Branches. They don't stand on their own. They occur as what? Branches. So you'll be seeing compounds like this. Let's look at common compounds and their namings, nomenclature. Let's go brother here. You have this C, 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 C. Class, one common thing they usually ask in Jamb chemistry is naming structure. I'll bring some questions too. It's time to visit our questions too. And then you have something like this, CH3. These are methyl now. This is a methyl group I just talked about, CH. They can't stay on their own because they're not complete. So they're usually attached to parents or complete families. And you have this. Let's start with this simple one first. Class is all called a parent name. When naming organic compounds with branches like this, it's all called a parent. The parent name of this compound now is butane. This 1, 2, 3. So the parent name of this compound is what? Butane. Butane. 1, 2, 3, 4. How do you get the parent name? The longest continuation of carbon without any obstruction. For class, apart from these 4 carbons, there's someone that is occurring branching on carbon 2. Is branching on what? So it's going to be called a branch. And this person is methyl. That's why I first started by recognizing him under the alkyl family. I just showed you now that the alkyl family CH3 is methyl, C2H5 is ethyl, C3H7 is propyl, C4H9 is butyl, C5H11 is pentyl. Can keep going on and on and this pentyl, this butyl. See how the enemy end with YL, but 4, pent 5, propyl, 3 carbons, ethyl, 2 carbons, methyl, 1 carbon. So class, if you are naming this, first of all, this is butane, but this is a branch, methyl group. CA3 is methyl. You're not going to say, what number does the branch for? Number 2. So say 2 methyl butane. 2 methyl butane. 2 methyl butane. That's the name of this particular organic compound. 2 methyl butane. Now, class, if we have another, we could have added another CA3 here on this same carbon 2, but below. Meaning that we now have methyl occurring twice, methyl occurring on the same carbon 2. For this kind of compound, we're going to say 2,2-dimethyl butane. 2,2 what? Dimethyl butane. 2,2-dimethyl butane. You know why we say 2,2? Because we have methyl group on carbon 2. We still have another methyl group on carbon 2 again, class. I know you might say, so why don't you just say 2? Should be 2 is still 2. Why don't you just say 2 instead of saying 2,2? No. In organic chemistry, F must be specific to detail. 2 for this, another 2 for dimethyl, show that there are double methyl groups. And the parent name still remains butane. Class, when naming organic compounds, the parent name is usually the one that ends the naming, butane. And don't forget, the parent name is the longest continuation of carbon without any obstruction. Look at, we have 1, 2, 3, 4 without any obstruction. 2,2-dimethyl butane. Class, we can keep going and have other branches like this. We are asked to name this. This is a chlorine group introduced there. And this is a Ca3 group introduced there. And this is a bromine group introduced there. Class, is assumed that when they give a compound like this, any space that is not in there, just know that it's hydrogen that is there. It's hydrogen that is. Anytime you see all these spaces, fill them with hydrogen. It's hydrogen that is going to fill up the spaces. Class, naming this, we are going to have, there are 3 branches present here. First of all, get your parent name. There are 5 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4. Class 5 means what? Pentane. So the parent name of this organic compound is pentane. Forget about the branches for now. Get your parent name first. This will be the end thing of the name. Every other thing should come before pentane. We're not going to say who are the branches. We have bromine. Class, in this Br means bromine. But class, when using it as a brand, we call it bromo. Cl means chlorine. In branches, we call it chloro. And obviously, this is still methyl we have used here, right? Methyl. Class, it's important when naming organic compounds. So we have 3 branches: bromo, chloro, methyl. Class, it's important that you mention B before C and before M, because alphabetically B comes before C and C comes before. It is wrong to say chloro, then bromo, then methyl, or methyl, then chloro, then bromo. Class, when naming organic compounds, alphabetical order must be maintained. Must be what? So we have bromo occurring on the first carbons. We're going to say 1 bromo. 1 what? We have chlorine occurring on the second carbon. We have 2 chloro. 2 chloro. And methyl occurring on the second carbon. 2 methyl. Pentane. The parent name still remains pentane. So we have 1 bromo, 2 chloro, 2 methyl, pentane. Write this down and let me take 1 or 2 questions on your Jamb past question. Please, if you're in this Jamb class, go and get checkpoint Jamb past exam question. It's up to date. It contains all your courses there, even mathematics, biology, physics, chemistry. Checkpoint. Get it. The name is checkpoint. Miracle, are you listening? You say you forgot the name. Checkpoint. Tell them to give you checkpoints. Eh? Tell them to give you checkpoint. That's the name. Okay, you see, I told you I've already seen one in Jamb now. We have to name this. C, 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 C. And you have Cl here, you have Cl here. You have H here. This on your Jamb pass question. Class, if I were you, every day, if you are writing Jamb, every day you should be able to solve 1 year of Jamb pass question every day. Solve a full year. If today in your personal timetable you are reading chemistry, say today I'm taking 1 full year of chemistry. Get Jamb pass question. Make sure you are soaking yourself in preparation. Very important, class. You can't say you're writing Jamb and you don't charge yourself up with the exam questions. Feel yourself solve. Every day, 1 Jamb question must go down. Tell yourself, have a target. Till Jamb reach, till the day of Jamb exam, every day, 1 Jamb pass question must go down. Every day, 1 Jamb pass question must go. If today you are reading chemistry in your personal reading, I must do 1 year. Complete 1 year. Tomorrow I'm doing biology, 1 year. Are we together? I want you all to get your pass question because very soon we'll start a series in which every day we'll agree on 1 Jamb pass question we're going to go and do. The next day will come. The first 1 hour will be to revise. There's no way you keep doing this. You will not do well in your Jamb. The ones you don't understand, bring it to class. That's why thank God you have registered for a class now. We'll then demystify it together, break it down for you. Are we together? Because that's the fastest way of preparing for Jamb. Because at some point I'll be digressing to exam questions too, because you see that if you finish just one topic, it will take a lot of time. But it's more specific if you go to the exam questions. What I'm also be doing is anytime, even if I want to cover some of these key topics, 1 hour might be for teaching, another 1 hour will be to visit exam questions. Because exam question is more direct, so you can balance from both. Do you understand? You can balance on both sides. But if you're just teaching, the Jamb is so vast, so broad, that you might finish teaching even up to half and you have not reached where they will even bring out. So as you're doing teaching this side, covering this side, you also go to tough questions in the Jamb question and solve. Explain how they solve it, teach it. Do you understand? So that you can cover all our bases. So look at this now. So the difference between exam and what they're teaching you and as simple examples. So we must also endeavor to be taking exam question, tough exam question like this now. Okay, look at this now. The number of isomers that can be obtained from C4H10 The number of isomers. That's not isomerism. So it's broad. It's broad. Too many things. But when you're doing the jam question, to remind you of things to teach too. Because there are so many things in chemistry. This is isomerism. This number 20, what? He said the number of isomers that can be obtained from C4H10 is just straightforward. A, 3, B, 4, C, 1, D, 2. We all know that the answer is 2. The answer is what? Butane has 2 isomers. I'll teach you isomerism. Butane has what? 2 isomers. I keep looking at this mic because once it goes off, and the video is recording, anything I'm saying is not, that's the disadvantage of this mic. It's good though, but the battery doesn't last so long. Once it goes, but what I need to study is how long does it take before it goes off, so I can also plan myself. Once it goes off, I've had videos that I'll be teaching. Then after a while, I'm not hearing myself again. I'll go and watch you say. So students are not hearing anything you're saying because the mic has gone. It will not even disconnect and say, okay, let normal voice be playing. It will just nothing. You will not hear anything. So it's very dangerous. So you have been teaching, and nobody's hearing anything. That's why I'm always looking at the mic. So class, I'll give you a formula that will help you to determine the number of isomers an organic compound can produce. Those that were in 100 level before here in this class. Remember I've given that formula before. Do you remember the formula? Or you have forgotten it? It's 2 raised per n minus 4 plus 1 plus. This formula will help you to deal with this question without stressing yourself. For this question, the Jamb question said, determine the number of isomers this compound will produce. This is butane, right? C4H10 is butane. The number of isomers an organic compound can produce is given by the formula 2 raised by n minus 4 plus n means number of carbon. Where n means number of what? Carbon. N means number of carbon. How many carbon does C4H10 have? 4, right? So that will be 2 raised to power 4 minus 4 plus 1. 2 raised to power 4 minus 4 plus 4 minus 4, 0. So that's 2 raised to power 0 plus, what is 2 raised to power 0? 1. 1 plus 1, 2. You see that the answer is what? 2. Simple. So while we are teaching, we should also be visiting exam. Because I can show you some tricks, some things that you will not be able to show in teaching. That is exam question that will make me show you what to do. You understand? In exam situation, exam question will help me show you a real exam situation. Sometimes I feel like teaching is just teaching for knowledge sake. If you just want to know things. Some people know things, but they cannot pass exam. Because exam is a different ball game entirely. It's a different field. You can see people are intelligent, but they still fail exam. So we must balance this. Even when I'm teaching you, we also go to exam questions. So exam question is straightforward, no small story, straight to the point. If you know it, you know. If you don't know, you don't know it. Let's name this. We have to name this. We have to name class. Naming this, what's the first step in naming? I said, get your parent name 1, 2, 3, 4. Class, when naming organic compounds, it's not compulsory it must be number 1. Any of this carbon can be number 1. You can say this is 1, 2, 3, 4. But class, there's something that I'll tell you soon. There are always different ways of counting, naming carbons or counting carbons in organic compound. Class, counting from this side, you have 1, 2, 3, 4. And counting from this side, you have 1, 2, 3, 4. Counting from this side, you have 1, 2, 3, 4. And counting from this side, you have 1, 2, 3, 4. Class, which side are we going to go with? Let's find out. Class, of course, no matter where we counted from, our parent name is 4, butane, right? We are sure that it is what? Butane. That's our parent name. But determine your parent name first. When you want to name an organic compound, determine your parent name first, butane. Now, secondly, you have 2 chlorine groups here on carbon 4. And you have, these are the branches, and you have 1 OH group. Let me circle out all the branches. Class, if we are counting from this side, we are going to have, OH means hydroxyl. So we're going to have 2 hydroxyl. 2 what? Anytime you see OH, it means hydroxyl. So this 2 hydroxyl. And counting from this side, 1, 2, 3, 4, it means that this 4,4 dichloro. 4,4 dichloro. As if we're counting 1, 2, 3, 4. But if you are counting 1, 2, 3, 4, we're going to have 1, 1 dichloro because this chlorine will now fall on carbon 1. 1, 1 dichloro. Counting from here, 1, 2, 3. So this hydroxyl will now be three what? Hydroxyl. Class, the question now remains, which of them is correct? Class, if you add 1 plus 1, what will you have? 2. 2 plus 3. Total number of branches here is 5. But if you add 2 plus 4, 6. 6 plus 4. Total number of branches here is 10. Class, we have less number here than here. So total number of branches here is 5. Total number of branches here is 10. So ideally, class, we should go for the one that gives us a lesser total number. But class, there's one exception. Class, if it wasn't that it was hydrogen that was here, if it was bromine that was here, bromine and chlorine belong to the same family. No one is stronger than the other. They're all halogens. They're all what? Halogens. But class, this hydroxyl group is stronger than chlorine group. So it's going to be given higher priority. So class, we're not just looking at the total number and who is lesser. We're looking at the hydroxyl group. This one has hydroxyl group on carbon 2. And this one has hydroxyl group on carbon 3. Who is lesser? 2 is lesser than. So we'll go with the one that makes our priority functional group lesser number. The numbering that gives our priority functional group a lesser number is what we're going to go with. Class, even though this, when you add 2 plus 4 plus 4, you have a total number of 10 is bigger than 1 plus 1 plus 3, 5. This total number is 10, is bigger than 5, right? Ideally, we should go with the lesser number. Total number is 5 here. But class, because hydroxyl group is stronger than this chlorine group, we are going to dismiss this chlorine group and focus on the hydroxyl group. But then again, class, this naming is still wrong. We shouldn't mention H before chlorine, see? So the correct naming should be 4,4-dichloro. Chlorine should be alphabetical order. Remember I told you that? 4,4 what? Dichloro. 2 hydroxyl. Then what's the parent name? 4 carbons. Butane. 4,4-dichloro. 2 hydroxyl. Butane. Yes. You see? Yes, it can be written in another form. It could be written like this: 4,4-dichloro butane 2-ol. Butane. Class, instead of saying 2 hydroxyl, this hydroxyl, class, the presence of an hydroxyl group in an organic compound automatically makes that organic compound an alcohol. Automatically makes that organic compound an alcohol. Meaning that you can end it with ol, butane 2-ol. That means the OH group is on the second carbon, so it's butane 2-ol. Class, the presence of hydroxyl group in an organic compound automatically makes that organic compound an alcohol. So class, if I don't want to say 4,4, she asks whether we can write it another way. Yes. Instead of saying 4,4-dichloro 2-hydroxyl butane, notice that this 2-hydroxyl is no longer here, but it's inside as 2-ol. Because OH makes you an alcohol. Class, the presence of an OH in an organic compound can make the ending of your name be ol. And where is the ol located? Carbon 2. So this OH is what's causing the ol. But if you don't want to mention ending with ol, then you mention the hydroxyl separately. 2-hydroxyl, then end with normal butane. Butane. You're not wrong. If you say 4,4-dichloro, you don't want to say butanol, but you say 2-butanol, you're not wrong. 2 what? This is also correct. 4,4-dichloro, 2-butanol, you are also correct. 4,4-dichloro, 2-butanol, you are also correct. Now, write down and let's take isomerism. You see that the Jamb has reminded me to teach you what? Isomerism in organic compounds. Isomerism. The good thing we are about recording this class, anybody that joins us as we are proceeding, they will not come and rejoin us back because there's a video, right? I'll just tell them, okay, you have missed organic chemistry, take. So that you know that in this class you will never be drawn back. Nobody will come, and no matter who a letter comes to join. Because when the exam is now getting close, they'll now start remembering that they have Jamb exam. By that time now, we'll just send them this video. Now, okay, we have taught this topic, we have taught this topic. Go to the YouTube channel and watch it, then join us where you continue. So nobody will come and then we'll not start from the beginning again. No. Nobody will draw us back. We'll just send you the video. As I'm always checking this mic to make sure that it's not off. Once it goes off, Anything I'm teaching is not recorded. It will be recording on the video, but the audio will not play. Isomerism is an occurrence in organic compounds in which organic compounds show similar molecular formula but different structural formula. Isomerism is an occurrence in organic compounds. Isomerism is an occurrence in organic compounds. Isomerism is an occurrence in organic compounds showing similar molecular formula. Showing what? Similar molecular formula, but different structural formula. But different what? Structural formula. Showing similar molecular formula is an occurrence in organic compounds showing similar molecular formula but different structural formula. Showing similar molecular formula but different structural formula. Class, we have types of isomerism. We have what we call chain isomerism. We have positional isomerism. We have functional group isomerism. And we have geometric isomerism. Class, there are still more types, but for Jamb's scheme of work, we have these 4 types for Jamb's scheme of work. Because we still have optical isomerism, we have stereo isomerism, we have enantiomers, we have anomers, we have epimers. I think those doing Chem 216, 200 level, we must have said, I don't know if they're teaching all those things yet. Anomers, epimers, epimerism. So organic chemistry is very broad, so that even university students of 300 level are still studying it. 200 are studying, 300 are studying, is very broad. Class, this chain isomerism is peculiar in the alkane family and is the most popularly asked in your Jamb syllabus. It's the most popular in your in the Jamb syllabus, and it's typical of the alkane family. It's typical of the what? Alkane family. Note that for the alkane family, isomerism begins from the 4th carbon member. Isomerism begins from the 4th carbon member, that is butane class. So the first 3 members of alkane family do not exhibit isomerism. The first 3 members of the alkane family do not exhibit isomerism. The first 3 members of the alkane family do not exhibit isomerism. The first 3 members of the alkane family do not do what? Exhibit isomerism. So isomerism starts on the 4th carbon. Another thing you should notice that all organic compounds are, every organic compound is an isomer of itself. Every organic compound is an isomer of it. So if they ask to list the isomers of an organic compound, class, the first isomer you mention is the organic compound itself. When you want to list the isomers of an organic compound, the first isomer you should mention is the organic compound itself. Don't forget that isomerism is when two compounds show the same molecular formula but different structural formula. That means they have the same molecular formula. What is molecular formula? That means they have the same number of carbon and hydrogen. So one person can be C4H10, the other person C4H10. When it now comes to drawing their structure, they now look different. But they have the same formula. For example, butane is C4H10. That's what they asked in that Jamb question. Butane is C4H10. Class, this butane is called N-butane. N means straight chain. N means what? Class, when an organic compound is not branched, it's straight chain. So an organic compound can either be straight chain or branched chain. So we use N to represent a straight chain part or isomer. Class, as soon as a branch occurs, an isomer is formed. Class, how is a branch formed? One of these carbons in this straight chain is cut off to come and form a branch at the center. Class, a branch is clearly seen because it will be in between the carbon chain. Remember that this is CH3. It now comes to form a branch here. And a different organic compound is formed, class, but still having the same number of carbon and hydrogen as butane. That's why it's an isomer. This compound and this compound, they have the same number of carbon and hydrogen, but different arrangements. In this arrangement, class, the four carbons are laid out straight. But in this arrangement, three of the carbons are straight, while one of the carbon is what? Branched. And it has a different name. So this will be 1, 2, 3. This is propane now, no more butane, pro. But who is the branch now? Methyl. This guy is now a branch because it's not part of the main chain again. And what number does the branch fall on? 2. So this is 2 methyl propane. Class, this is the second isomer of butane. The first isomer of butane is butane itself. The straight chain form of butane is the first isomer of butane. The first isomer of every organic compound is the organic compound itself, yes. In alkane family, yes. So methane, ethane, propane do not exhibit isomerism. So butane is the first. So as I say, isomerism starts from the first fourth carbon. Class, so the two isomers of butane is N-butane and 2-methyl propane. And we gave you that formula to determine number of isomers. 2 raised per N. Please don't forget this formula. Minus 4 plus. This formula works for chain isomerism, which is chain isomerism in alkane family. This formula works for chain isomerism, which is isomerism in alkane family. Class, let's look at positional isomerism. Before we go to positional isomerism, let's still look at the isomers of pentane. How many isomers of pentane? Butane is pentane. Let's look at isomerism in pentane. Pentane means 5 carbons. If I'm to use the formula 2 raised by n minus 4 plus 1, n is 5 because pent means 5 carbons. So 2 raised to power 5 minus 4 plus 5 minus 4 is 1. So 2 raised to power 1 plus 2 raised to power 1 is 2. 2 plus 1 is what? It means that pentane will produce 3 isomers. Pentane will produce what? 3 isomers. Let's look at the 3 isomers of pentane. Let's look at the 3 isomers of what? Pentane. So the formula has told us that to produce 3 isomers. Let's now apply. Don't forget the first isomer of every compound is a straight chain from M-pentane to, so just draw 5 straight carbons. Draw 5 straight. Obviously, each of these spaces are filled up with what? Hydrogen. We know that pentane has 3 isomers. So if this is the first isomer, there are 2 more, right? When you exam, because which of following is not an isomer of pentane in the options below. So they'll give you 3. Jamb has 4 options, A, B, C, D now. They give you 3 correct isomers, but pentane has 3 isomers, and put 1 wrong isomer. So the straight chain pentane is the first isomer of pentane. The second pentane, cut one of these carbon and make it a branch. Because if you want to make a carbon a branch, it cannot be in any of these ending carbon. Because if I cut this carbon and I put it here, class, it's still the same thing because it's still 1, 2, 3, 4. So don't think that it's only when this carbon are straight like this that they are straight. No. This carbon can be like this and it's still correct. Please take. So when you want to make this carbon a branch, it cannot be in any of this ending carbon. If you also brought this carbon and put it here, it's still correct. It's still straight. You just repeated the same thing. But this 1, 2, 3, 4, 5 is straight. So straight doesn't mean that it must just be like this. If it comes like this and then comes down like this, still straight, and even comes down like this, as long as you can see a clear continuation, as long as you can see a clear, there's no breakage whatsoever. But if you brought out this, remember this was 5 carbons. If you brought it out and put it here, there's a breakage. You cannot say 1, 2, 3, 4. Yes, there's a split already, right? It's not a branch here now. So, but let us not destroy this. This is a straight chain. I want to list the 3 isomers of pentane. This is 1. So let's say 1, 2, 3, 4, 5. The second one will be 4 carbons. We have cut off. Let's cut off this 1 carbon and bring it as a branch here. This CA3. So this is the branch now. So this is now 1, 2, 3, 4. This now becomes 2-methyl butane. 2-methyl. Because this is a methyl group. This is a methyl occurring on the second carbon. The parent name is butane. It's now 4 carbons. Bu. And this is a branch on the second carbon. So this is 2-methyl butane. 2-methyl butane. 2-methyl butane. But we know that pentane has 3 isomers. So I want to cut out another carbon. We need to cut out what? And put it here. And the third isomer is formed. But let me not cut it from here so that you can still clearly see the 3 isomers. So the third isomer of butane, of pentane, will be here. 1, 2, 3. And then you have CA3 here. You have under CA3. So this is 1, 2, 3. This is 2, 2. Di, because there are 2 methyl groups. Methyl. Now the parent name must be the ending. What's the parent name? 1, 2, 3. Propane. This is the third isomer of pentane. So the 3 isomers of pentane, therefore, are N-pentane. That's straight chain pentane. N-pentane. 2-methyl butane and 2,2-dimethyl propane. I'll come again. N-pentane. 2-methyl butane. 2,2-dimethyl propane. These are the 3 isomers of pentane. Now, this is what we'll do under what? Chain isomerism. When we come in our next class, I will continue from positional isomerism. I don't want this video to be too long, so I can upload. So we'll continue from positional isomerism and other types of isomerism. Like I said, as we teach a little, we'll take Jamb exam questions to balance it up. So class, we're going to meet in next on Thursday. Tomorrow is matric. So we're going to meet in next on what? Thursday by 4 p.m. Thursday by what? 4 p.m. So those of you that are following us online with our class, Organic Chemistry Introduction. So join us in the next class. We'll continue from here. Thank you very much.